Our adventures continue with equilibrium constants. Here we have a table with a bunch of different snapshots of containers that are all using this same reaction, where hydrogen gas reacts with iodine, which isn't normally a gas, but okay, and they combine to make hydrogen iodide. And they explain the containers are scorching hot, so at 448, apparently iodine is a gas instead of the usual solid. So we have blanks to fill in many of these rows. We don't have anything we need to find in row A, except we kind of do. We need the equilibrium constant, and they didn't give it to us. But we can find it if we have a nice row like this where they've given us all the other information. The K for this reaction should be the concentration of HI squared over the concentration of hydrogen times the concentration of iodine. So with row A, they tell us HI is 1. And I'm going to say don't forget to square it just because I really don't want you to forget those powers. But of course, squaring a 1 is silly. It just gives you 1. So mathematically, that's a waste of time. Hydrogen is 0.4. Iodine is 0.5. 0.4 times 0.5 is 0.2. 1 divided by 0.2 is 5. So our equilibrium constant is 5. Good. Now that we have that, that's valid for any one of these containers because they're all at the same temp. So now that we have that, we should be able to stomp the rest of these. So, row B, same formula, only now we know what the equilibrium constant is. We have our HI is 8.5. Don't forget to square it. Our hydrogen is 0.16. We don't know what our iodine is. You can call it X if you want to. I'll call it I just to be a little creative. And we know that has to come out to 5 because our equilibrium constant is always 5. So from this, we must solve it and find out what I, or X, is. How do we do that? There's a few different moves you can make here, like flip both sides, which is kind of a cool one, but in general, if you have a fraction and you don't like it having a denominator, you can multiply both sides by whatever the denominator is. So in this case, if I multiply the left by 0.16i and I multiply the right by 0.16i, a lovely thing happens. These cancel out, leaving just 8.5 squared. This might feel a little freaky because you're trying to solve for I and you just destroyed it, but it's okay. You created another copy on the right at the same time, so the I is not lost. So having done that, we're left with 8.5 squared, which a calculator can do. That's 72.25. Equals 5 times 0.16 is 0.8, and we still have I. We want I alone, but it's multiplied by 0.8. What's the opposite of multiplying by 0.8? Divide by 0.8. And same thing over here. 0.8's cancel, and we get I equals 72.25 divided by 0.8 is going to be just over 90. Yeah, 90.3125. And this is a concentration, so moles per liter. And for sigdigs, this had 2, this had 2. I should have kept sigdigs for my equilibrium constant. This should actually have come out to 5.0. Sorry about that. That that looks like a retcon because it is, but I promise the numbers that went into finding the equilibrium constant had 2 sigdigs, therefore this has 2. So we can afford to give 2 in our answer, and we can say 90. That's a minor sin right there. They left an extra digit in the constant. Right? So that's how we solve for a missing iodine, and now we get to do the whole thing again for a hydrogen. Let's make some space. Okay. new one. HI is 3.75 now. Don't forget to square it. Hydrogen, don't know. We'll call it H. Times iodine's 0.333 equals, and it has to come out to 5.0 because that's our constant every time. Again, if you want to knock out your denominators, multiply both sides by 0.333H. And on this side by 0.333H. These cancel, so we have no more denominator, and we're left with 3.75 squared, which is 14.0625. And on the right side, we get 5 times 0.333, which is 1.665. H. Want H alone? Unfortunately, right now it's multiplied by 1.665, so do the opposite. Divide both sides by 1.665. Didn't give you enough space to work on this, and now I am punished for it because I have to work in the same small space. 14.0625 divided by 1.665 gives us 8.4459. 8.4459 moles per liter. Again, because of the limitation on the equilibrium constant, this should be trimmed to 8.4. Again, I was too generous in the key on significant digits. Sorry for that. 8.4 is where that should have gotten trimmed. But I hope the calculation makes sense. Okay. Then they go back to unknown iodine. This won't be too different from question B, actually. So our HI concentration is 22.4. Don't forget to square it, you know. Hydrogen is 356. Iodine, I called it I before to show how creative I am. I'll just go with X this time. And we know that has to come out to 5. So again, if you don't want a denominator, multiply both sides by 3.56x. And here we multiply by 3.56x. Cancel, cancel. And we get 22.4 squared, which is 501.76. 5 times 356 is 17.8 times x. So we want x alone, it's multiplied by 17.8. If you want to get rid of that, divide both sides by 17.8. That cancels, and we're left with x equals 501.76. Doing the calculations in real time means you get to mess up in real time. And we get 28.18 moles per liter for the concentration of iodine. If we cut that to 2 sig digs, we should get 28 moles per liter, so yeah, too many digits one more time, and surely it'll happen again in part E. Okay, final round. Scientific notation is a little annoying. I think I'll turn those into regular numbers when I write the expression. So, here the HI concentration is unknown. We can call that X just to have a name for it. So X, don't forget to square it, over, this is 400. The iodine's also 400. This is a pretty high pressure container. If you're fitting in 400 moles per liter of two different things, that's a lot of gas. And all this has to come out to 5. I mentioned a shortcut earlier. I will assume that you can do this using the direct method from before, where you multiply these together, multiply both sides by its square root. Here's a minor shortcut that you can sometimes use when these numbers are identical. Because these are both 400, you can rewrite this as x squared over 400 squared equals 5. And then, because these are both squared, we could square root the entire left side and square root the entire right side. And when you do this, this square root strips the square off the x, and it strips the square off the 400. When you square root a fraction, you affect the top and the bottom of it. So that's gone, that's gone. And so in lectures, you'll often see them do this, and then the next line they write is just x over 400 equals the square root of 5, which is like 2.23 or something, 2.2361. So they strip off two squares with a single square root, and it gets you to here. And now, if you want x alone, it's divided by 400, so your fix is multiply both sides by 400. Those 400s cancel, and we get x equals 894.427, etc. moles per liter. If we had to write this with two sig digs, you can't write 894 with only two digits, so you'd have to go to scientific, and that means you would say 8.9 times 10 to the 2 moles per liter. So you don't have to love this method. I don't use it a lot myself, but it very much does work, and I've definitely been in classes where they've done this move. So if you're watching stuff online or if you go on and do more chemistry, you'll see people do this, and now you know what they're up to. So hope that was reasonably comfortable, and we'll see you next time.